I welcome you all for the discussion on experiment number 3. In this experiment, we are going to discuss how to find the Taylor series expansion of the given function. We are going to write the Python code for obtaining the Taylor series expansion of the given function. First, let us discuss what do you mean by the Taylor series. Suppose if you have any function y equal to y of x, which is continuously differentiable at some point, say x naught, then we can express this function as a polynomial of degree n or as an infinite series or a polynomial of infinite degree. So that such expression or such series expansion is known as Taylor series expansion. So the advantage of Taylor series is to write the given function y of x, which is continuously differentiable at the point x naught, as a polynomial. Okay, how the for Taylor series expansion of the given function looks like? See, it is of the form y of x equal to y of x naught plus x minus x naught divided by 1 factorial into y dash of x naught. I have to find the first derivative at the point x naught plus x minus x naught whole square by 2 factorial into y double dash of x naught. Similarly, you have to write the successive terms. So the next term will be x minus x naught whole cube by 3 factorial into y triple dash of x naught. So in general, you can write the general term as x minus x naught whole power n divided by n factorial into y n of x naught plus and so on. So this is called the Taylor series expansion of the given function. If you simplify these RHS, then this will be a polynomial of degree n. If you restrict for only n minus 1 number of terms, or else it will be a polynomial of degree infinity. This helps to approximate the given function in terms of a polynomial. For example, we can approximate sin x in terms of a polynomial, similarly cos x, log x, e power x. Wherever the function has continuous derivatives at the given point, you can approximate that function, the values of that function by a polynomial. That is the advantage of Taylor series. So this Taylor series we sometimes called as Taylor series of the function y of x about the point x naught. Sometimes we say this is the Taylor series expansion of the function about x naught, or sometimes we say in powers of x naught. In powers of, we write x minus x naught in powers of x minus x naught, or the Taylor series expansion at x equal to x naught. All these three statements implies the same series. So these three statements are equivalent. If you are asked to write the Taylor series expansion about x equal to x naught, or in powers of x minus x naught, or about x naught, all refers to this series expansion only. Okay. Now we have a particular case of this series, that is at x naught equal to 0. Suppose we obtain the Taylor series expansion at the point 0. That has some speciality. Okay. Such series, which is of the form y of x equal to y of 0 plus x by 1 factorial into y dash of 0 plus x square by 2 factorial into y double dash of 0 plus, you can write the general term as x power n by n factorial into y n of 0 plus and so on. This is called the Maclaurin series. So Maclaurin series is the special case of Taylor series. Maclaurin's series. So we can obtain the Maclaurin series by taking x not equal to 0 in the Taylor series expansion. So this is the introduction about the Taylor series and Maclaurin series. So in the next part, we shall discuss how to find or how to obtain the Taylor series expansion by Python. Okay, how to write the Python code to obtain the Taylor series expansion of the given function. That is our task in this experiment. Okay, if you look into the procedure, let me write here. What are the steps we have to follow to write the Taylor series expansion or the code for the Taylor series expansion? So first you have to define library functions. You have to call the library function. Looking into the concept, if you want to just find the Taylor series expansion, then I have to choose which library function I have to choose. I mean, you have to call for. If you want to draw the, plot the graph of the series, then I have to call different library function. So looking into your constraints, you have to call for the library function. That is the first step, calling the library function. Then define the function. Define what is the given function. Define y equal to what. That is the next step. In the third step, you have to write the code format just to format the predefined values. So then in the fourth step, I have to define what is x naught. What is x naught equal to. Then find the derivatives. Find derivatives. Then simplify it. To find the derivatives, we use the code diff of y comma x. Y comma x refers to the dependent variable here. In the first place, you have to write the dependent variable. Here, you have to write the independent variable. Which function I have to differentiate should be written in the first position. With respect to which variable I have to differentiate should be written in the second place. Then I have to simplify the expression. We just find out the derivative there, but it is not simplified. So to simplify that, the next step is simplification. So we write the code lambdify. Here I have to be careful because in this code the syntax is first you have to write with respect to which variable you have to simplify the expression, then which expression you have to simplify. Okay, then I have to write the lambdify, then write the expression for series, then write the series. This is the steps, these are the steps you have to follow to write the Python code for the given function. See here also, if you wish to find the Taylor series expansion of the function, first you have to look into what is the function. Then you have to look into the point at which we need to obtain the Taylor series expansion. Then you have to find these derivatives y of x naught, y dash of x naught, y double dash of x naught, y triple dash of x naught, depending on the problem statement. You have to find the derivatives. After finding the derivatives, you have to simplify it. Okay, sometimes you get expression like say secant x into tan x by secant x. So by finding the derivative, you get this expression. By simplification means you have to cancel the terms, so you get tan x. So from this step to this step, what we do, that is done by the code lambdify. Okay, then after obtaining all the derivatives and simplifying it, you just write the formula for the Taylor series and substitute the values, then you get the required Taylor series expansion. Okay, now let me write the code for the Taylor series expansion. The first question is, find the Taylor series expansion of sin x about the point x equal to pi by 2 up to fourth degree term. So that is the first question I am going to consider. So in this question, we need to find the Taylor series expansion of sin x, the function y equal to sin x. So first I should call the library function, then I should define y equal to sin of x. Then after defining that, I should write this code format. Then I should write x naught. So for this x naught, I should write pi by 2, right? So generally I'll write float of pi by 2. So then what are the library functions required? Since I'm using variables here, you have to call simpy, right? Since I'm using variables, you had to call simpy. Then, since I'm using this pi and all, then I should call numpy. So right now, it's enough if we call simpy and numpy. Those two library functions enough for our discussion. If you wish to plot the graph of the function, then I have to call matplotlib. So that is optional. Let us call it later. Now let me write the Python code to find the Taylor series expansion of sin x about the point x equal to pi by 2. Right. So now just I'm launching the Python, I mean Anaconda and then Jupyter Lab. Here we are going to write our code. Okay. Let me take a new console. So here is the cell. So as I said earlier, first I should call numpy and simpy. For numpy, import numpy as np. This is the standard format we generally use. For simpy, you can write import simpy. That is one way. Another way, from simpy import star. From simpy import star. So this library function contains more instructions than just import simpy. So practice to use this library function from simpy import star. This syntax you have to practice. So when you define simpy, you have to define the variable you are going to use. Okay. So x is the variable I'm going to use. So x equal to, I'm just writing only one variable here. So I should write symbol with S capital. If there are two or more variables, then I should write symbols with small s. Okay. So x. So I just define the independent variable. Then the function y equal to, let me write sin of x. Sometimes we may need to write 1 star x within bracket. Now time being, I just write sin of x. Then as I said, format to clear the predefined value. Then define x naught. So what is x naught? X naught equal to float of pi by 2. So we have defined x naught also. So the next is finding the derivatives. So let me find the derivatives. Dy, that is derivative of y with respect to x. So I'm asking the Python to differentiate y with respect to x. So dy equal to diff of y comma x. Differentiate y with respect to x. Then d2y I'll write. So d2y, I can write diff of y with respect to x twice. You can write this, or you can just write differentiate dy with respect to x. That also will give you the second derivative of y with respect to x. Then d3y equal to diff of d2y with respect to x. Here the question, they are asking to find the Taylor series expansion up to fourth degree. So I should write one more term. D4y equal to diff of d3y comma x. So look into the steps. First we called the library functions. So in this step we called the library functions. Then we define the symbol. Then we define what is y. Then format. Then we defined what do you mean by x naught. What's the value of x naught. Then we found the derivatives. Now we have to simplify these derivatives, right? So for that, I'll call y naught equal to lambdify of x comma y. I'm just simplifying y with respect to x. Then I'll call this as y1. We have y dash, right? So I'm just writing y1 for the first derivative. So that is lambdify of with respect to x. I have to simplify the expression dy. Then I have to write the same expression y2 here, y2 equal to lambda phi of d2y, then y3, then y4. Okay, now we have simplified the derivatives y0, y1, y2, y3 and y4. Next I have to write the formula for the Taylor series expansion. Again you can use y, nothing wrong, or if you want you can use another variable. Say let me use f, or let me use w. So w equal to y of, sorry, y naught of x naught. So here is y naught, right? Simplified expression. So y naught of x naught first term plus second term. I will open double bracket. X minus x naught whole over 1. It's not necessary to write. X minus x naught by 1 factorial. That is also not necessary to write. So I have to write y1 of x naught. Okay. Plus double bracket. X minus x naught whole square divided by 2 factorial, that is 2 star y2 of x naught plus x minus x naught whole cube by 3 factorial, that is 6 into y3 of x naught plus x minus x naught whole over 4 by 4 factorial, that is 24 into y4 of x naught. So this is the Taylor series expansion of the given function. Now I have to print this. So for that, I'll write print within single quote or double quote. You can use both the syntax, single quote or double quote. The Taylor series, don't use apostrophe here. The Taylor series of the given function is, I have to simplify w, then print it. Simplify of w. Simplify of whatever the variable I have written here, same thing should be written here. So when you ask the Python console to print the Taylor series expansion, it will print you the output. Okay, let me run it. It's still running. Look into this time. Okay. So this is the Taylor series expansion of the given function. Okay, this is how I have to write the Python code to generate the Taylor series of the given function. Okay, this is one part. So if we look at the question, they are asking to find the value of sine 100 degree. So we need to find some particular value from the series. Okay, we can also find the particular value of the given function and the value from the series. Then we can verify whether those two values are same. We have obtained the Taylor series expansion of sin x. We have Taylor series here. From this, you can compute the value of sin 100. You get some particular value. You can compute the actual value. Then you can verify whether those two values are same. See, if you want to write the expression or Python code for the Taylor series expansion of cos x, just replace sin x by cos x. You get the Taylor series expansion of cos x. If you want to write the Taylor series expansion of log x, let me check whether you get the output. Yes, we are getting the output. If you want to write the Taylor series expansion of exponential, then also we are getting the output. Just to change the function y. If you want to obtain the Taylor series expansion of the function, okay, let me say sin x only at different points, say at pi by 4, suppose I want to find the Taylor series, then just change the value of x naught. You get the different value. So now in this way you can get the Taylor series expansion of the given function. Okay. Next part is finding the particular value from the actual function and the series. Let's check whether those two are equal. From the series, you can compute the value, but I have to first mention which value I have to substitute in the series. Okay, for that I will call T1 equal to, we have to convert it to radian. So 100 into pi by 180. Pi by 180. So I am taking T1 to be 100 into pi by 180. Okay. Now I'll ask this to substitute this value in the expression W. So W1 equal to W, in which expression I have to substitute the value that should be written here. So W dot substitute to which variable you have to substitute that should be written here, comma, which value you have to substitute that should be written here. Okay, T1. So I'll substitute the float value of T1. Okay, so the substitution will be done. Then let me print the value. The value of sin 100 from the series is, I have to print the simplified value of W1. So 0.980864 something. So this is the value of the sin 100 obtained from the Taylor series. Okay, let me check what is the actual value of sin 100. Print the actual value of sin 100 is sin of float of T1. Let me check whether we get the output. Otherwise, I have to write float of sin. Okay, yes, we got the output 0.98480. See, there is an approximate difference 0.9808, 0.9848. So we get only the approximation of the given function. We don't get the exact value. I mean, exact value in a interval of short length. Okay. Next, there is one more part. If you wish to draw or plot the graph of the function, then these are the commands you have to write. First, you have to import the library function required. Okay. From matplotlib, or let's write import matplotlib dot pyplot as PID. This one we have practiced even in experiment 1. So in the next section, I mean in the next lines, we are going to write the Python code to plot the graph of the actual function and the series. Okay. So first I should define the function. Define f of x. So what should be f of x? That should be written here. So return in place of f of x sin x. Let me now just write sin x. If we get an error, then I should write sin of 1 star x. Okay. So it is now defined. Then I have to give the limits for x, right? So limit x equal to lim space of minus 5 to plus 5. How many interval? Oh, sorry. How many subintervals you want? You can write here. I say I want 1000 subintervals. Then after giving the value for x, you have to plot the graph. So plt dot, okay, there is one more code missing. I had had to simplify the expression and call that value as y80. Y80 equal to simplify. Okay. Since I am simplifying the mathematical expression, if you write lambdify, which will have to lambdify the series, that is W. So y8 equal to lambdify of x comma W. Now PLT plot dot PLOT plot x comma independent variable I had to write. Then which function I had to plot, that I had to write here. To identify which curve is referring to which function, I should label it. So label equal to graph of the series. You can write any sentence within single quote. The same thing will be printed. Next, PLT dot plot x, comma, which function I have to print? F of x, comma. Now label it as actual curve. Or actual graph, you can write anything. Then when you label the curves, you have to print it. So for that, you have to write the code plt dot plot. Okay, legend. Then plt dot show. Check for a minute. Linspace right here. np dot sign of 1 star x. And now let me run the program. Yes, we got the graph here, but it is taking arbitrary values for y. I'm not getting whether it is properly approximating the given curve or not. So for that, I have to restrict the values for y. So I'll write plt dot y lim of, take the limits of y to be some, say, minus 2 to plus 2. Now running it. Got the actual graph which we are expecting. If you want grid, plt dot grid of, okay. So this is the graph I'm getting. Okay. This is the Taylor series expansion of the given function. So this is how we have to write the code for the Taylor series expansion of the given function. Thank you.